Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 22 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 2338. Count the number of ideal arrays. So let's read the problem statement first. You are given two integers n and max value, which are used to describe an ideal array. A zero-indexed integer array of length n is considered ideal if the following conditions hold. Okay, every array of I value, okay, from 1 to max value. Okay, so every element, okay, in my array, it should be from 1 to max value. Okay, max value is given to us. All right, and every array of I is divisible by array of I minus 1. Okay, and I from 0 to n. We have to return the number of distinct ideal arrays of length n, and since the answer may be very large, we have to return it modulo 10 raised to power 9 plus 7. Okay, now see this example number 1. Okay, let's understand this problem statement with example number 1. Okay, n is equal to 2. Okay, so we have to form array of size 2. Okay, and the max value that we can use is from 1 to 5. Okay, so we can use 1 2 3 4 and 5, but we can't use 6 7 8. Okay, we can't use all these numbers. Okay, from 1 to 5 we can use anyone. Okay, so here the following are the possible ideal arrays. Okay, so arrays starting with the value 1. Okay, 5 arrays, so like here 1 and 1. All right, so here divide this 1 is completely 0 by 1. Okay, so here array of I. Okay, so 0 1. Okay, so here this is 1. Okay, so array of 1, it should be divisible by array of 0. Okay, so 1 is completely divisible by 1. Okay, 1 divided by 1, so you are going to get 0 remainder. Okay, so it is completely divisible, right? Okay, and same here 1 2. Okay, so this 2 is completely divisible by 1. Okay, 1 into 2, you are going to get 0 remainder. Okay, same way 1 3 1 4 1 5. Okay, so the array starting with value 1, total 5 arrays are there. Okay, and all are having length 2. Okay, then array starting with value 2, so 2 arrays, so we have this 2 2 and 2 4. Okay, so 4 divided by 2 completely divisible, 2 divided by 2 completely divisible, but here 2 3 3 is not completely divisible by 2, right? So this is not valid. Okay, so but these two are ideal arrays. Same way starting from 3 we have this 3 3. Okay, this is only valid. Starting from 4 we have 4 4. Array starting with value 5 we have 5 5. Okay, so there are a total of 5 plus 2 plus 1 plus 1 plus 1, total 10 distinct ideal arrays. So 10 is my output. Clear? Now see example number 2. N is equal to 5 and max value is 3. All right, so here if you see in this case, we have to form array of length 5. Okay, and we can use number from 1 to 3. Okay, until here only, we can't use any other number, right? So here first choice array starting with the values 1, so they are 9. Okay, so we can use 1 1 1 1. Okay, this one. Okay, right? Then after it, okay, this is one. Then with second distinct value, okay, so we can use this. Okay, all are starting from 1 only. Here also this is also valid, right? 2 is completely divisible by 1. Okay, so here 2 is completely divisible by 1 and 2 is also completely divisible by 2. Okay, so this is also valid. Okay, and same way this is also valid, this is also valid. Okay, so with second distinct value 2. Okay, 1 we are using and one more distinct value 2 we are using. Okay, so here single 2, 2 2s, 3 2s, 4 2s we are using. Okay, so all are valid. Okay, with second distinct value, okay, 3, then they are 4 s, right? Here 1 1 1, then 3. Okay, 3 3s, 4 3s, then okay, until here only 4 we are not seeing, right? Then array starting with the value 2, so from 2 this is only valid. Okay, and then starting from 3 this is only valid. So there are total of 9 plus 1 plus 1, 11 distinct ideal arrays. Okay, so 11 is my output. All right, and these are the constant size. Okay, so before jumping to this problem, let's discuss about few topics. First is, what is this basic arithmetic versus modular arithmetic? So basic arithmetic deals with standard operations on numbers like addition, subtraction, multiplication, and division. Okay, so here let's see this division. Okay, so if I'm dividing this number a divided by b, okay, so a, let's suppose a is 17 and b is 5. So what is the output I'm getting? I'm getting 3.4. Okay, a divided by 5, I'm getting 3.4. But in modular arithmetic or clock math, so it finds the remainder when one number is divided by another. Okay, here we are not getting the remainder. Okay, but here we are getting the remainder when we use modulus. Okay, so a modulus with b. Okay, so it's like wrapping around a circle. Think of a clock. So a mod n, a modulo n means the remainder when a is divided by n. Okay, so like 17 mod 5 you use, so you are going to get 3. Okay, you are going to get the output as 3 but remainder as 2. Okay, so you need just remainder here. Okay, so here 17 divided by 5. Okay, 5 into 3 15, and here remainder is 2. Okay, that's what I'm saying here. Okay, and 23 mod 7 2, and here 10 mod 3 remainder is 1, 14 mod 7 remainder is 0. Okay, so real life example, like you can say clock example. So let's suppose it is 9 o'clock right now. Okay, let's suppose it is 9 o'clock right now. Okay, so here 3 6 and 9. Okay, 9 o'clock. Now I ask you guys that what is the time after 5 hours. Okay, so what you are going to do, from here it is starting again 1 2. Okay, so you are going to say that after 5 hours it will be 4, it will be 2. Okay, right, it will be 2 after 5 hours. But how you can simply calculate this? 9 plus 5 14, and then you know that we have time from this 0 to here until 12. Okay, so total 12. So 14 more 12, you are going to get 2. Okay, so it will be 2 o'clock. Okay, because in clock we have 12 intervals, right? Here 1 2, okay, 3 4 5 6 7 8 9 10 11, and here 12. Okay, until here. So 14 more 2 12, if you do, you get 2. Okay, so that is the answer. Okay, so this is nothing but modular arithmetic. All right, now what is this NCR? Okay, so NCR read as n choose r. Okay, so is the number of ways to choose r items from n items without considering the order. Okay, so let's say you have 3 books named as A B C. Okay, so here n value is, let's suppose 3. Okay, now I ask you guys to choose 2 books. Okay, you can choose any 2 books. Okay, so this is one way that you choose A B, or you can choose AC. Okay, or you can choose BC. Okay, is there any other way to choose 2 books out of 3? No. Okay, so here what is the formula of this NCR, which is nothing but number of ways to choose r items from n items. Okay, so here if I apply the same thing here, 3 C2, and here n factorial is 3 factorial, and r factorial is 2 factorial, and here 3 minus 2 factorial. Okay, so what is the output that I'm going to get? 3 into 2, here 2, and here 1 only, so this will cancel out. So 3 is output, and here you see only 3 are the valid, right? 3 is valid answer, right? So this is the formula for NCR. N factorial means the factor of n means the factorial of r, and n minus r means the factorial of n minus r. Okay, and here C5C2, if you calculate, you get the same output. Okay, then here, okay, one more thing, this r should be greater than n. Okay, r should be greater than n. Okay, then NCR is going to be 0. Okay, so if r is greater than n, then NCR we are going to say 0, because you can't choose more than available items, right? And NC0 value is 1, and NCN value is also 1. Okay, so in programming contexts, modular arithmetic is used for large n. So you will be often compute NCR mode. Okay, using modular inverse. So now what is this modular inverse? Okay, so we are going to discuss this. Actually, we are going to use all these things in today's problem, so that's why I'm discussing all these items first. Okay, so now how you calculate this modular NCR? That simply means NCR mode, okay, with mode. Okay, so let's say this mode value is 10 to the power 9 plus 7. So when n are big, so n factorial can be huge, so we can compute NCR under a modulus, typically like this. Okay, that's a mode is this, which is a large prime number often used in competitive program. Okay, so usually we see this number only, right? 10 to the power 9 plus 7. Okay, so here formula is NCR mode. So this NCR formula you already know. We are going to do mode with this mode value, okay, which is given to us, right? But division under mode is not direct. Okay, so we convert division into multiplication with the modular inverse. Okay, so here I can write this like this now, n factorial, then I will bring this r factorial to the top. So that simply means r factorial, and here I will write minus 1. Same way I can bring this n minus r factorial to top. So I can write it as n minus r factorial, okay, and here on top -1. Okay, so this is what I'm doing. Okay, and then mode here. Okay, NCR mode. Okay, done. Okay, division under mode is not direct. Okay, division under mode is not direct, so we convert division into multiplication with the modular inverse. So that's why I convert this. All right, now how are you going to compute this NCR mode? Okay, so first here there is one formula. Okay, so pre-compute factorials up to n. Okay, so we will just compute all the factorials up to n. Okay, and you already know how we calculate the factorials. Like 1 factorial is 1 only, 2 factorial is 2 into the factorial of 1. Okay, right, and 3 factorial is nothing but 3 into the factorial of this 2 factorial, that is nothing but 6. Then 4 factorial is nothing but 4 current number into the previous number, 4 minus 1, 3 factorial. So 4 into 6, you are going to get 24. Okay, so this is a okay, so we will just pre-compute all the values up to n. Okay, so that we can directly get the value of factorial. So and compute modular inverses using Fermat's little theorem. Now this is a new thing. Okay, so I will discuss about this as well. What is this Fermat's little theorem? Okay, so if mode is prime, okay, so what we are going to do, a, okay, inverse. So let's suppose this some value. Okay, it's like we are taking the inverse. Okay, so a inverse mode, how we calculate this value as a mode -2 and then here mode. Okay, so I am going to write this a -1. Okay, whatever I am bringing here as a mode -2. Okay, because we can't calculate the negative. Okay, negative mode. Okay, we can't calculate that, so I'm going to write it like this. Okay, so now how this value is coming? Okay, so this is your next question. So here first, let's suppose if I want to apply brute force. Okay, how it works to find the modular inverse of a. Okay, modular inverse of a under modulo m. Okay, that's pair, let's suppose modulo m. Okay, so what we have to do, we have to find an x such that a into x mod m is equal to 1. Okay, so here let's suppose you are calculating 3 inverse mod 11. Okay, you are calculating this. So what is the value of this one? Okay, so how you calculate this? Okay, so here what we are going to do, we have to write it like this. Okay, 3 into, and here we have to search for the x value. Okay, so first let's suppose you say that 3 into x, x as 1. Okay, and then take the mode with 11. Okay, so 3 mod 11, you are going to get 3 here, right? You are getting 3 here, 3 mod 11. Then you are going to get here you are getting the mode as 3 only, right? Here same way, 3 into 2, 6. Okay, 3 into 2, 6 mod 11, you are going to get what you are going to get a different mode. Okay, so 3 into here 2 value. Okay, so 6 and mode 11. Okay, 6 modulo 11, so here you are going to get 11,006 as the remainder, right? So this is the remainder that is coming up. Then 3 into 3, if you take x value as 3, so 9 modulo 11, you are going to get 11. Okay, but if you take x value as 4, you are going to get this one. Okay, so 3 into 4 is equal to 1. Okay, so this will be valid. Okay, so here LHS is equal to RHS. So you are trying all the values of x starting from 1. Okay, and make sure when we are going to get this one. Okay, so with the value 4, you are getting 1. Okay, so inverse of 3 mod 11 is 4. Okay, so this is the what we need to do in brute force. Okay, to find modular inverse of a under modulo m, we have to find an x such that a into x mod m is should be equal to 1. Okay, so this is the formula actually how we calculate the inverse. Okay, so this is brute force. Okay, if I apply this formula and calculate all the values of x, then it is going to take of m time complexity. We are trying all the values from 1 to m minus 1. Okay, until it finds the modulo inverse. All right, so this is going to very slow if mode is large. That's why 9 plus 7 not suitable for programming code tests or large n. All right, now what is this Fermat's little theorem? Okay, so Fermat little theorem says that we can write this a minus mode as a mode -2 simply. Okay, so module inverse of this a raised to power mod minus 2 and then just mod. Okay, so this is going to remain the same. Okay, so here a minus 1 we can simply write it as a mod minus 2. Okay, so this is going to become a positive number. Okay, and positive number we can easily find, we can easily get the remainder when we are going to divide it with the mod value. Okay, so here with this Fermat's later theorem algorithm, if you just apply this formula, okay, so time complexity is going to be of log mod, okay, using fast explanation, much faster. Okay, so why this time complexity is coming up? Let's see. So find 3 mod 11. Okay, same example. So you are going to get 311 minus 2, 3 power 9. 3 power 9 is nothing but 19683, and you are, when you are going to do the mod, so you are going to get directly value 4. Okay, so here how we are checking 3 1 3 2, okay, 3 3 3 4 and until 3 9. Okay, so here see directly we can apply this formula 3 power 9. Okay, so modular inverse of 3 mod 11 is 4. Matches brute force result but done with faster using exponential. So we are just using this exponentiation, right? 3 power and mod minus mod value is 11, 11 minus 2. So we have to just apply this 3 power n. Okay, 3 power 9. So this is going to give the result in logarithmic mod time complexity. Okay, so that's why this is going to be fast. Okay, so this is nothing but my what Fermat's little theorem. Okay, so we are going to use this as well in our code. All right, and now okay, so I have already discussed about this binary exponentiation, right? So here see 3 power 9. So are you going to write it like this, 3 into 3, 3 into 3? Okay, so you are writing this 3 how many times? This many times. Okay, n times. So if this number itself is very large, let's suppose 3 power 2000, very large. Okay, so you going to write this 3 2000 times? Okay, so that is going to give O of n time complexity. Okay, very large. Okay, let's say n. So this value very big. So are you going to do this? No. So now to overcome this challenge, we are going to use binary exponentiation. Okay, so I have already discussed about this previously, but let's see what it is. Okay, so binary exponentiation computes, or we also say this fast exponentiation. Okay, so a power b mod m efficient, it calculates in of log b time instead of ob. Okay, so here ob time. Okay, so this time ob time, let's say, which is super useful for large values of v. Okay, so here what is the core idea behind this? So instead of computing a power b by multiplying a b times, we break the exponent down by bits. Okay, so b 13, we are going to write it like this 1101. Okay, so 1 2 4 8. So here see this is nothing but in binary form I writing now. So this is nothing 13. Okay, so here at 3 we have value, so 2 power 3 we are just going to add at here we have 1, so 2 power 2, and here 2 power 0. Okay, so if I can write a of 13 as a of 8, a of 4 and a. Okay, so this we can do, we multiply powers of a only when the corresponding bit in b. Okay, so I have already explained this, but is fine fast exponentiation. Okay, so if n value is even, okay, if n value is even, then you can write it like this. Okay, so let's suppose 3 power 6. So you can write it like this now, 3 power 6 divided by 2, you are going to get 3, and here you can write it like this. This is also valid, right? But if 3 power is odd, okay, let's suppose, then you can write it like this, 3 into, okay, and here 3 7 minus 1 6. Okay, here a 3 power 2. Okay, you can write it like this. Okay, so if n is even, so we can write it like this, and if n is odd, just extract 1 3 extra here, and then same. Okay, this reduces the power by half in each steps. Okay, so now what you are doing here, you have to calculate just this. Okay, 3 power 3, right? And you can further reduce it. Okay, so let me show you how. So let's suppose you are calculating 3 power 13 modulo 100. Okay, so you can write it like this, 3 into 6 mod here power 2. Okay, and here 1 3 extra because 13 is odd, right? And same way you can further reduce it, like 3 power 6 you can write 3 power 3 into 2 here. Okay, then after that you can further reduce this. Okay, so you can write here 3 into 1. Okay, this 3 into 3 na, 3 power 3, 3 power 3. Okay, so you can write it like this na, 3 into 3 power 1 into 2. Okay, so here this is what you are going to do here. That's it. Everything else is remain same, right? So 3 power 3, this part only you are changing it like this. Okay, so this is done. Then same way you can further reduce it. Okay, so here see how easily we calculate this. Okay, we are not writing 3 13 times. Okay, so here in just logarithmic time complexity we are using this. Okay, So here, see this tree diagram that we have made. Okay, so in the end you are going to get some output here, right? So this is the recursive way, okay, recursive code. Okay, so I think we have solved this problem related to this fast explanation, I think 1 week back. Okay, so in that we are using this recursive approach, recursive code. Okay, so it's very easy. Like here you have one a value, n value, and mode value. Okay, so if n is equal to 0, okay, so if 3 power 0, so you have to simply return 1. Okay, and otherwise you have to do the half of it. Okay, so in the next process, a I am passing the base value, and exponent value I'm dividing it in half, and the mode value. Okay, and the result value, what I'm going to do, half into half modulus, okay, divided with the mode. Okay, modulus with mode. So if it is odd, then I'm taking the result as uh, here result into a, okay, the extra value, that here we are taking the extra value. Okay, modulus with mode. Okay, so if this is odd, then we are going to use this. Okay, and in the end we have to return result. Okay, so every time I'm doing the half here. Okay, so see here, like here 3 power 13, if you apply this formula, so 3 power 13, then you are reducing it like this, 3 okay, you are reducing this part, 3 into 3 power 6, okay, and power 2. Okay, so this is very easy, just go over this. Okay, we have already I have already shown you this in one previous code. Okay, so you can take a reference from there. Okay, so this is the recursive way. Okay, and this is the iterative version of this same thing. Okay, and this is how you calculate the modular inverse using Fermat's LeetCode theorem. Okay, so you need to calculate mode inverse. Okay, so whatever number I'm going to pass, so you have to just uh, going to do the binary explanation. Okay, so here, like, this is your base and this is your power. Okay, so you have to just write mode minus 2 here. Okay, and this is the code for recursive binary explanation. Okay, so here how you calculate this, so this is also very easy. Like, so recursive binary explanation, okay, same thing that I explained here. All right, so take 313 and some mode value, very big value. Okay, so right now this value is equal to 0. No, it is not equal to 0. So what you are going to do, you are going to get the half, and next time you are going to pass it as 3, and here you are going to pass 6. Okay, 3 power 6 you are going to pass. Then next time again you are going to pass 3 power uh, 3. Okay, next time, and okay, this is done. Then next time you are going to pass 3 power 1 here. Okay, and the next time 3 power 1 when you are going to do. Okay, so again you have to reduce in half. Okay, so here actually 3 power 6. Okay, so you are just dividing it in half. Okay, so you are going to solve this part. So here if you see, you are solving this part in the next process. Okay, let me use green capacity. Okay, 3 power 6 you are writing first. Okay, then you are solving this further. Okay, so you are writing 3 power 3. Okay, into 2 you are reduced by outside. Okay, then here you are writing 3 into 3 power 1 power 2. Okay, 3 power 1, here see it is coming. Then after that, here 3 into 3 power 1 is 1 only, 3 only. Okay, so 3 into then 2 2. Okay, so here now it is very easy. Now 3 into 3 you are going to do, so 3 into 3 you are going to get 9. Okay, 9. All right, this is done. Okay, 3 power 2 here, this 3 power 2. Okay, you are going to get 9 here, and then 3 into 9 you are going to get 27, and then you solve 27 power 2. Then 27 power 2 is 7 to 9, and here this will come. Okay, 3 into, okay, so like this. Okay, so just go over this. So this is easy, and then the same code I'm using here. Okay, uh, this for binary explanation, and we will pre-compute the factorials and inverse factorials. So this is also very easy. So I already told you how we calculate the factorials. Okay, factorial of I is nothing but factorial of I minus 1 modulus multiplication with I. Okay, so like 3 factorial is nothing but 3 into that current number 3, and here factorial of previous number, like it is 2 factorial. Okay, so this we already know. So this is how we calculate the factorial, and we just do the mode because values can be very large. Okay, and inverse factorial, how we are going to do, we are going to call the here mode inverse and factorial of n, we are going to pass value. Okay, so we are going to iterate from the end. I is equal to n minus 1, I should be greater than equal to 0, and I minus 1, and here inverse factorial is nothing but inverse factorial. Okay, and here of I plus 1 into I plus 1 modulus Okay, modulus with mode. Okay, so this is what we do. All right, so and we already know how we calculate the mode inverse. Okay, so here mode inverse we are going to calculate. Okay, so this is what we need to. Okay, so now just jump into the main part of this problem. Okay, so, but we are going to use all these codes in our code. Okay, so I will also explain by writing the code this one, but let's first understand how we are going to get the output. Okay, first let's understand the approach. One more thing here, don't get puzzled why I am writing like this: inverse factorial of I as inverse factorial of I plus 1, next one, and I plus 1 modulus with mode. Okay, so don't get confused here. So let me show you how actually we are driving this. So I have yeah, here see this. Let's say n is equal to 4. Okay, to keep it simpler, so factorial of 0 to 4, you are going to get factorial of 0, you already know 1, factorial of 1 is 1, factorial of 2 is 2, factorial of 3 is 6, factorial of 4 is 24. Okay, and this is going to my fact array, right? 0 1 2 3 4. Okay, so now we have to calculate the inverse factorial of 4. Okay, so inverse factorial of 4, okay, we are going to calculate as mode inverse of fact 4. Okay, so this is nothing but mode inverse of this 24. Okay, because factorial of 4 is 24, right? So how we calculate this? So mode inverse of this 24, we can call this bin power. Okay, so this fast exponentiation, right? So here you are going to pass the x value, that is nothing but 24, and here the mode value -2. So see, this is what I'm doing. Okay, and I'm calculating this, so we will get something like this. Okay, right, using faster binary explanation, right? So now how we are feeling this rest thing? Okay, so why are we are using this factorial root? Okay, so here what does it mean? In fact, factorial of 3 is factorial of 4 into 4 plus 1. Okay, so I plus 1 here. Okay, so how this is coming? So this is actually it is coming. So I plus 1 factorial, we already know that current number and previous number factorial. Okay, like 4 factorial, you know that it is nothing but 4 into 3 factorial, this we already know, right? So how this recursive relationship is coming? Okay, this for loop. Okay, so here what I did, okay, so here take modular inverse of both sides. Okay, so modular inverse I took for the both sides. So here took mode inverse of both sides. Okay, -1 and then after that I am multiplying both the sides with I plus 1. So here if I multiply both the sides with I plus 1, so here this, see, this is also I plus 1 inverse. So if I am dividing multiplying with I plus 1, so this and this I plus 1 that I am multiplying will cancel out each other, right? Okay, so here this is going to cancel out, so only left with this. So see, this part only left out with this, and in this part we are adding one more I plus 1. Okay, because we are multiplying with I plus 1 both sides. So now here inverse factorial of this I, now see, this inverse factorial of this I is nothing but inverse factorial of this I plus 1 and I plus 1. Okay, mode, so which is exactly what your code does. Okay, so that's why I'm using this for loop. Okay, so I hope that this is clear, and this already we know, right? Binary explanation, how we calculate. Okay, all right, and then after that, now let's understand how our code is working actually. So n is equal to 5, max value is 3. Okay, so we have to form the arrays of size 5, right? And max value that we can use is 3. Okay, we can use 1 2 3. All right, so first of all we are going to set this max length is equal to 14. Okay, so here it is saying that this number should be completely divisible by this number should be completely divisible by this. Okay, so here let's suppose, here if you see yeah, here why max length we are taking is 14, because even with the smallest divisor 2, okay, starting from 1, okay, so 1, and here next number let's suppose 2 power 1. Okay, next number let's suppose 2 power 2. Okay, because we are dividing it with 2 now. Let's suppose next number is 3. So here see, we are getting until 8192. Okay, so this is given to us, right? Max value to 10 to the 4. Okay, here I'm taking the smallest divisor possible, so we can't build a sequence of valid divisor longer than 14 within this range. Okay, so this constant size is given, right? So every time we are dividing this current number with I minus 1. Okay, and make sure that complete is well. So here with 2, okay, if we are taking smallest divisor, then also it is not possible with having greater length than 14. Okay, so that is why we are taking this. All right, max length is 14. All right, so here this is clear. Then dp array, you already know why we are taking +1 and +1 here, because the values are starting from 1. Okay, then we have to build the dp to build all the chains. Okay, so what does this mean? So here first of all let's suppose dp of I. Okay, I is a number, okay, with which my current chain is going to end, and the length of that particular chain. Okay, so length of particular chain, it is saying that just one. Okay, length, this is nothing but, let's suppose, length. Okay, and here the number is ending with 1. So here with this, how many results are possible? So only one result is possible with this. Okay, so here if you see, only if we use just single one. Okay, so with single one, only one result is possible. Okay, same way with if we use a length one and this two. Okay, so this is some chain, so with this chain ending at this two. Okay, so only one result is possible. Okay, single two, I'm not talking about double twos here, I'm talking about single two. Okay, of length one. Same way with three also, single result is possible, right? So this is what we need to do, dp to build all chains. Okay, so from here we will get to know the value of dp of 1 comma 1 as 1, dp of 2 comma 1, okay, of length 1 ending with the 2, 1, dp of ending with 3 of length 1 is 1. Okay, so max value is 3. Okay, until here only. Okay, so this is done. Okay, this is going to be my step 1. Now let's see for length 2 what we need to do. Okay, so here max length value given, we will take 14, and max value until 3 only given to us, right, in this case. So here what does this mean? Okay, so let's understand. So with the length of 1, okay, so they are just single elements like 1 2 3 in this case. Okay, so total 3 were there, right, ending with just 1. Okay, 2 here and 3 here. Okay, now here length of 2. Okay, 2 chains. So we are going to build a chain AB where B is a multiple of A, right? So this is what we need to do. So only these two are possible, right? 1 2 and 1 comma 3, right? 3 is a multiple of 1. Okay, only these two. So now here dp of 2 2 is going to be 1. Okay, because of this 1 2, and dp of 3 by 2 is also going to be this. Okay, so ending with 3 of size 2, ending with 2 of size 1. Okay, so here ending with 2. Okay, ending with 2. Okay, of size 2. So here if you see this 1 2, just 1. Okay, ending with 1. Okay, this just this one. Okay, so this is clear. All right, this is clear. Okay, now after that, here length of 3 chains. So a b c we need to take, right? So b is a multiple of a, then c is a multiple of b, so all values should be less than equal to max value. So if we start with this 1 2, can we extend? No. Okay, we can't extend, right? 2 multiple is 4 6, so we can't take all this, right? We have to take the smallest, right, multiple, like c should be multiple of b, right? So we can't do that. So with this 3 there are no chains possible, right? So if you see with the length 1, these are the 3 chains possible. With length 2, these are the 3 chains possible, right? So we know these chains, right? Now we are going to calculate for each chain of length this, the number of ways to place it in an array of size n is going to be n minus 1. Okay, size will be decremented and length will be decremented. Okay, in this we have to place. So how we calculate this? So length of one change. Okay, one chain. So 1 2 3. So how total here 3 chains. Okay, and we already know what are those 3. And with the 2, length 2, so total 2 chains, right? So here ways to place each in array of length 5. So there are total 4. Okay, 4 here, right? And you are going to get total contribution as 2 into 4 8. All right, and here with the length 3 you're going to get 0 contribution. Okay, so here let's see how these are coming actually, right? So here it is saying that with just 1, contribution is 1. With the 2, we already know that contribution is 1. With 3, contribution is 1. So it is saying that with 1 2, the contribution is 4. Okay, so let's see where is this 4 contribution. Okay, 1 2. So see, this is one contribution, this is one contribution, this is one contribution, this is one contribution, and this is one contribution, total 4, right? Now here if you see 1 3, total 4 contributions. Okay, so here if you see with 1 3, 1 contribution, 2 contribution, 3 contribution, and 4 contribution. Okay, so we are just placing those chains, right? We are just finding out the number of ways, so we know this. Okay, so now how many limited places we have where we can move this chain? So that is nothing but n minus 1, and here length minus 1. Okay, so for this also we are going to write one code. Okay, one piece of code. All right, so here if you see this okay, so initializing like this, then dp table we already know dp of 2 2 and 3 2, we are going to get 1. Okay, so ending with 3, length 2, ending with 2, so we already know how we are getting this. Okay, and with this it's not possible, so I just skip this. Then we are going to just pre-compute factorials and factorials, inverse factorials, because we are going to use that. Okay, so now to understand this, let's see this piece of code. Okay, how we are going to calculate the valid arrays. So okay, here I'm taking the result variable as 0, and then I'm running loop I is equal to 1, I is less than max value, okay, I plus plus, and here length I'm taking, okay, 1 to max length, only this, and here we are calculating the ways and the result. Okay, so here let's understand this with, okay, this thing. Okay, so here for value is equal to 1, length is equal to 1. Okay, so dpu 1 value we already know 1, and ncr 4 comma 0 we already know that this value is 1. So contributions, how we are calculating this into this, so we are going to get 1 and result is 1, and we already know the y1 is coming. Okay, value is equal to 2 of length 1, so for this also only one contribution. Okay, so chain ending with 1, chain ending with just single 2, okay, chain ending with just here length 1, okay, only this. So here value is equal to 2 and length is equal to 2. So here we are just going to use this formula that here we have written, right? dp of I into length, the ways. Okay, how we are calculating the ways. All right, so here you are going to put this like dp to 1 and ncr 4 1. If you apply this formula, contribution is going to 4 and result is equal to 6. Okay, so value is equal to 2, okay, ending with this value 2 and length 2. Okay, so how many different ways, so you are going to get that. Okay, so you have this, right? Total 4 you are going to get. Okay, we already discussed somewhere here. What are those? Where is that? Like here 1 2, okay, 1 2, okay, ending with 2 1 2 1 2. Okay, then same way here value 3 length 1, so you have just one contribution for this value 3 length 2. So value 3 and length 2, this contribution, this contribution, this contribution, this contribution, yeah, 4 contributions here. So you are just doing the addition here, so result is 17. Okay, so this is the code for this. All right, so now we are going to use these only same things, okay, in the code. So let's move to the coding part, and then you guys will get much clear idea, okay, when we are going to write complete code for this. But this is what we need to do. Okay, so now let's write the code for this problem. First of all, what you need to do here, create the mode value, okay, which is given to us like 10 to the power 9 plus 7, static finder, and here int, and take the mode value as 10 to the power 9 plus 7. So you can write it like this 1, and here 1 2 3 4 5 6 7 8 9. Okay, done. Then after that, create one dp array as discussed. Okay, so here int dp. All right, and then you have to calculate the fact and inverse fact. Okay, so for that, just create one d array int fact and inverse of fact. Okay, this is done. Then after that, inside this ideal arrays, okay, inside this, first of all, what is max length? Okay, max length we have to give it as 14. Okay, so we have already discussed about this, because since max value is 10 to the power 4, so the longest chain is logarithmic of 2 10 to the power 4, which is going to approximately give us 14. Okay, and then just create one dp. Okay, just initialize it. So here new int, and here we are just pass the max value plus 1. Okay, since we are starting from 1, okay, so that's why plus 1 I'm using, and here max length plus 1. Done. Then after that, what is going to our first step? Step 1 is going to be build the dp to build all the chains. Okay, so here I'm just going to run one loop. Okay, int I is equal to 1, I is less than equal to here max value, and here I plus plus. Okay, so here inside this I will just apply dp of I and 1 equal to 1. Okay, this is done. Then after that, we have to iterate, okay, over all the values of from starting from length 2 until my max length. Okay, so here for loop int length is equal to 2, and then after that length should be less than equal to this max length. All right, and here length plus plus. All right, and here inside this you have to write for int I is equal to 1, I is less than equal to, and here you have to pass what max value. Okay, and here I plus plus. All right, and now inside this just do the multiplication, okay, for the next number that we are going to use. So int multiplication of this I into 2 Okay, and this multiply value, it should be less than the max value which is given to us. Okay, it should not cross that. So here max value, and then here next time the multiplication value is going to be multiplication plus here I, right? And now inside this just update the dp value. Okay, so dp of this value and here this length. Okay, all right. So here you have to write it like this. Okay, so here dp of mul and here length. Okay, and in this you have to add dp of I and here len minus 1. All right, and then just do the mod because value is going to be very large. Okay, so this is done. All right. Okay, now after this, once this is done, then my step 2 is going to be pre-compute the factorials and the inverse factorials. Okay, so here I will just call one method. Okay, so you can say pre-compute you can say factorials, and here I will just pass the n value. All right, and then our step 3 is going to be count the valid arrays. So for that, just create one variable long result is equal to 0 first. Okay, and then after that just run loops. Okay, that we need to run. Okay, for first int I is equal to 1, and here after that I should be less than equal to max value. Okay, and here I plus plus. All right, and then after that for int and here length starting from 1. Okay, and here this length should be less than equal to my max length which is given to us, right? And here length plus plus. All right, and then after that inside this just check first if dp of I and length value. Okay, so if it is equal to 0, then simply you can continue. Okay, no need to check further. All right, so you can continue here, and then we have to calculate the ways here. Okay, if long ways here we have to calculate. So how we are going to calculate? So just call this ncr. Okay, ncr, and here you have to pass n minus 1. Okay, and length will be len minus 1. Okay, from n minus 1 we have to choose this l length minus 1. Okay, right? So we have to choose positions now here inside this. All right, and then after that you have to just update your result. Okay, result is equal to the result value. Okay, plus, and here dp of I value. Okay, whatever the value that is stored here, dp of I, and here length, and you have to just multiply it with base, and then after that just take the mode. Okay, mode, and here overall values mode. Okay, modulus with mode, done. All right, so this is done, and in the end, okay, here your this for loop ends, so you have to just return. Since we have to return the output in int, so here you can write return, and here you can write int, and here just change it. Okay, results. All right, okay, this is done. Then after this it should be result, right? Okay, now this is done. All right, so now after that we already know the code for how do we calculate the factorials, inverse factorials, ncr. Okay, so all this stuff I'm going to write now. Okay, so pre-compute factorials and inverse factorials. So here just create one function void pre-compute. Okay, pre-compute factorials. Okay, so here let's take this c small, pre-compute factorial, spelling is matching, right? Done. Okay, and here you have to pass int n. All right, and here you already know how we calculate the factorial. Okay, so fact first initialize this array, new long, and here n plus 1 we have to do, right? And then inverse factorial we have to calculate, so you already know. So here also same thing, new, and here long, and here n plus 1 you have to do. All right, and you already know that factorial of 0 is going to be 1 always. right? And then just run one loop for int I is equal to 1, I is less than equal to n, and here I plus plus, and here inside this you have to calculate the factorial of I, okay, as factorial of I minus 1, okay, and here multiply it with I, and then you have to take the mode as well, okay. So here mode, okay. So in competitive exam we pre-calculate all these stuffs, okay, factorials, like stuff like factorial, okay, because it will save time. You can't again and again find the factorial of a particular number again and again. Just store them in array, okay. 2 factorial is this, 3 factorial is this, 4 factorial is this, everything store in one array, okay. And now let's move to the inverse factorial, okay. So first of all, let's write inverse of factorial, okay. So inv, and here factorial, okay, here of n, it is going to be mod inverse, okay. We will define this function mod inverse, and in this just you have to pass factorial of n value, okay. This is done. Now, okay, now we have to calculate the factorial from starting from n minus 1, okay, in the reverse order. So int I is equal to n minus 1, and your I, it should be greater than equal to 0, and I minus minus, okay. And here you have to write inverse of factorial of I is equal to inverse of factorial of I plus 1, and here you have to multiply it with I plus 1, okay. We know the next number I plus 1, and here you have to just do the modulus with mod, okay. So this value is going to be very large, so we have to do it every given time, okay. So this is done, this is code for this, okay. Now after that, once this is done, so we have to write the NCR method as well, okay. So how we calculate the NCR, that also you know already, okay. So NCR using pre-computed factorials we have to calculate, okay. So long, and here n, use capital C R, okay, and here int n and int r, okay. So here few base conditions we already know, right? Like your r value, it should be greater than 0, otherwise you have to, what you have to do, okay. So if here, if r value is less than 0, okay, or your r value is greater than n, then in that case you have to simply return 0, okay. And here otherwise just return, we have to just return what, fact of n into, okay, we already know this, inverse of factorial of r, because r is going to move up, right, as we already discussed about this, okay. Just take the mode of this value as well. So here mode, and then after that same way for n minus r you also need to do, okay. So you can just copy this, paste it here, and here you can write n minus r, okay, n minus r mode, right. So this is done. Now how you calculate the mode inverse, okay. So we have to write that as well, okay. So how we are calculating this mode inverse, so this is also very easy, okay. So long of mode inverse, okay, inverse, mode inverse. So here just pass, okay, modular inverse we are going to use using Fermat's little theorem, okay. So here we are going to write it like this, mode inverse, and here long x, all right, and here inside this we are just going to return, okay. We are going to use fast explanation or binary exponentiation, right. So here you are going to write binary BNPO, okay, binary power, you whatever you want to say, and here you have to pass the x value, and then here you have to write mode minus 2. We already discussed about this formula, why mode minus 2 is coming, okay. So x bar mode minus 2 mode we have to calculate, right. So this is the, here that is done, okay. Now we have to just calculate the binary explanation, that's it, okay, and our code is completed, all right. So here just write long bin bar Okay, and here you have to write like base you are passing and exponent you are passing, so you can write long, let's name it exp, okay, for clear understanding. And here if your exponent is, I'm going to use recursive approach here. All right, so here if it becomes 0, then simply return 1. All right, and take the half value as long half is equal to binary power. Okay, so here what you need to do, base, and here you have to divide it with half it, right? Divide it with 2. Okay, so this is done, and then you have to update the result is equal to binary power. Okay, here result nothing but half, whatever the half value you are going to get, half into half. Okay, half into half, and here just do the mode. Okay, mod d, right? And here if it is odd, so if exponent modulus with 2. Okay, if it is odd, then in that case you have to update the result as result into base. Okay, and here with the mode. All right, and then in the end you have to simply return result. Okay, so that's it. So now let's run the code and see if there are any code issues. We'll try to fix that. So yes, there are some issues. So here this is missing, I think that's the only issue. Let's see anything else. So yes, here 1 second, line number 32, 33 and 38 we are getting issues. Okay, line number 32 first. Here what you are doing, factorial, you are going to write it like factorial new long n plus 1. Okay, and here how you are taking the fact, you are taking the fact. Okay, let's change it to long. Okay, I'm using long now, values can be very large. Okay, so this is done. What was the other issue? Let me run it again and see. It's taking some time, let's wait. So see, all the test cases has been accepted. Now let's submit it. So see, our solution is accepted, right? So I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.